Okay, so this problem of restricted blood flow contains two of the concepts that we've just learned. We're going to both use the continuity equation and Bernoulli's equation. And this is sort of an application of one of the early videos I showed about how, plaque can build up in blood vessels and cause problems. And here's just some of the fluid dynamics behind it. So let's think of this little our blood vessel. Maybe I should draw it red. Think of our blood vessel. And it's got some restriction in it, some little bump in it like that, right? We're told that there's some fluid velocity in, and there's some pressure, P1 at this end. And we're interested in what happens at some point here, what the pressure is, and what the velocity is through this restricted region. And what we know is that there's a difference in areas. This is the area 1. And we know that the area 2 here, that this is going through, is 1/5 of A1. So this is a bunch of information we were given. Okay, so the first step is to use the continuity equation to find V2, right? We know that all of the fluid here is getting squished to some smaller area. So the continuity equation is the velocity times the area through one point is equal to the velocity through some area at some other point. And we can solve this for V2. A1 over A2 is equal to V1. And we're told that A1 over A2 is equal to 5, right? The ratio is 5 times V1, which means that our velocity 2 is equal to 0.6 meters per second. Given that we were told that this velocity up here, V1, was equal to 0.12 meters per second. Okay, so that's the first step. The second step is now to figure out the pressure going through this place. So in order to find the change in pressure, we're going to use Bernoulli's equation. And what Bernoulli's equation requires is for us to follow a streamline. And the streamline that we're going to follow is essentially some piece of fluid up here going over here. When we do this, we're going to assume that the change in height is essentially negligible in this. So if we write down Bernoulli, we have P1, the pressure at through surface 1, the pressure at point 1, plus 1/2 rho V1 squared plus rho GH1 is equal to P2 plus 1/2 rho V2 plus rho GH1. 2. And we're assuming that H1 is essentially equal to H2. So these cancel out. And we're left with P1 plus 1/2 rho V1 squared is equal to P2 plus 1/2 rho V2 squared. I'm just going to move this up, which implies that P2 is equal to P1 plus, and I'm gonna move this V2 to the other side, and then I'm gonna group a bunch of stuff together. So that's 1/2 rho V1 squared minus V2 squared. And if we use our numbers, we're told that this is 13,000 kilopascals or 13,000 pascals about, minus, it turns out that this difference is 183 pascals. If we plug in all those numbers, and we get this number, 13,417 pascals for our pressure at point 2. For part B, just quickly, the percent change is equal to the amount it changed divided by the original, right? So it's 183 divided by 13,600. So around 1.3% change in pressure.